So these are your mathematical practices for AP Calculus. This is the guideline that the calculus teachers have to follow, things that they need to make sure that you are able to do and apply in addition to the content. So I feel like it's also important for the pre-AP teachers, and which pre-cal kind of falls under that umbrella, even though this isn't a pre-AP class, because we still are preparing you for calculus. So it's a pre-calculus class, even though it's not a pre-AP class. Whether you take calculus in college or whether you take it in high school or whatever, these things still apply. It's not all about just AP calculus. It's just about calculus in general. So the first one, if you look at MPACS 1, says reasoning with definitions and theorems. We have things in here. It says use definitions and theorems to build arguments. Confirm that hypotheses have been satisfied. Apply definitions and theorems in the process. Develop conjectures. Produce examples and counterexamples. Where did you do all of this stuff? A whole lot. What class? Geometry, right? Geometry is a lot about theorems and hypotheses and conjectures and examples and counterexamples. And that course is designed to really strengthen your critical thinking and problem solving skills as far as that stuff is concerned. You may never again in your life have to prove two triangles congruent, okay? I'll give you that. But the types of things you did when you had to do that, the arguments that you had to make, the theorems that you had to use, the application of this stuff, that's the purpose of doing all that with that, is not just so you know about triangles, but so that you strengthen these skills, that you understand the importance of, if you know what the theorem says, the theorem is telling you how to solve the problems. And theorems are very heavy in calculus as well, and we'll have some too. But so that's what that is. I want you to jump to MPACS 3, down at the bottom of that same page. Select appropriate mathematical strategies. I talked before school today with somebody a long time about this, a student that was, we just kind of got off topic on this, but if I said to you, solve this problem and use this process, most of you could do it. You're like, I can do that, and I can do that process, and you do it, and x equals 5, whatever. The struggle becomes when you're looking at something and you don't know what the heck to use. Like, you have all these tools in your tool belt, but then now you have to decide which one to use when, and that a lot of times is the bigger struggle than the actual process itself. And so that there are times where we force you to struggle so that you can struggle through that so you feel more comfortable making those decisions. But sequence algebraic computational procedures logically. Complete algebraic computational processes correctly. Like, these two things here basically means you got to be able to do algebra. The algebra is what's going to kick your butt in this class and in calculus as well if you don't have super strong skills. Apply technology, okay, kind of referring to the calculator mostly, strategically to solve problems, not just to add and subtract, but when it's required, because you don't get it all the time in calculus either. Attend to precision, being exact and saying what you really mean, and being exact with your numbers and stuff, and not just, well, you know what I meant, that was kind of close, that sort of thing. Then jump to 5, and we'll come back and refer to some of these others throughout the year, but know and use a variety of notations. Connect notation to definitions. Connect notation to different representations. Notation, right? Clearly present methods, reasonings, justifications. Accurate and precise language and notation. So we talked about notation yesterday, right? And you being able to communicate your conclusion. Your conclusion on number 16 yesterday wasn't -4. Your conclusion is that P of -8 equals -4, right? And so I want you to see this because I want you to understand when I'm being nitpicky about that stuff has nothing to do with my opinion. It's not that it's my pet peeve that you're not writing this. This is my guideline. If I don't do that, I'm doing you a disservice. Does that make sense to you? Because if this doesn't get focused on at all until you hit calculus, you're going to struggle with that and the content. So this really, honestly, should have been focused on with you more along the way than it has been for a lot of you, but this is why I'm doing that. So, and we'll refer back to these and see how we're connecting them so that you have what you need to be successful in your future maths, okay? All right, so just put that aside for now. We'll talk about where that goes in your ISN in a minute, and let's look at our notes. So, continuity and in behavior. And this is going on page 30, and we're done. Now, everything up until this point, with the exception of maybe increasing, decreasing, has been review. You wouldn't know it by the likes of your quizzes, but it was a review. And this is new, but it's not crazy difficult. So continuity, that is a form of what word? Continuous, or to continue, right? So continuity. So we're looking at whether or not a graph is continuous. So it says a graph is said to be continuous if there are no blank or blank in the graph. So if I put my pencil down on the far left-hand side of this function and I trace along, if I can trace along the whole thing without picking up my pencil, it's continuous. If I got to pick up my pencil at any point to start back over or whatever, then it's not. So a graph is said to be continuous if there are no breaks or holes in the graph. So if there are breaks or holes in the graph, what do you think the opposite of continuous is? Discontinuous. Okay? Discontinuous. Make sense? So it's either continuous or it's discontinuous. So it is or it isn't. So there are three main types of discontinuity. So we're going to look at here. Now, a graph can have more than one at a time. It can have all three types at one time, or it can have them individually like they do in these examples here. So this first one says, when f of x increases or decreases infinitely as x approaches x equals a from the left or the right. So here is x equals a. As x approaches this from the left, right, it's going to decrease infinitely. As x approaches a from the right, now this is the first time we've gotten to go left on the x-axis, but we are looking at what happens when x goes this way as well. So when I'm approaching it from the left, it's going to increase infinitely. So on that graph, what actually exists on the graph at x equals a that's not drawn in? An asymptote. Very good. It's an asymptote. So there's an asymptote here, right? So that's what makes it increase or decrease infinitely when it hits there. This is called infinite discontinuity, or it can be called asymptotic discontinuity, which is a strange word, but that's what it is. So because this thing right here is an asymptote. Okay. But that is infinite discontinuity. Now, the next one, when f of x jumps from one point to another at x equals a, so I'm tracing along my graph. When I get here, I got to pick up my pencil and I got to jump up here to keep going, right? First of all, is this a function? Yes. When I snap it back together, this is an open circle and this is a closed circle. So if I snapped it together, I don't have any overlaps there, right? I can do my vertical line test and it's going to pass the test since that's an open circle. So look at the domain. Is your domain continuous or does the domain break? What do you think? The domain is continuous. All the x's, all real numbers would be your domain, right? Every single x all along the way is included in there, even though the graph itself is not continuous. Does that make sense to you? You can have a continuous domain and a discontinuous function. All right, so this right here, since I jump, and it is discontinuous, this is called jump discontinuity. See how easy that is? Jump discontinuity. Now, when f of x is continuous everywhere except for a hole at x equals a, it's like I had a line and I took a point out, right? So think about it as removing a point. That one point on that line has been removed from the graph, so this is called removable. Removable discontinuity. Everybody good so far? Those are the three. A graph can have more than one at a time, but those are the three that exist. Are we good? All right. So let's look at the examples then. It says determine if the function shown on the graph is continuous. If not, identify the type and location of discontinuity. So let's look at number one. Is this continuous? No. So what type of discontinuity? Jump. So we're going to say that it has jump discontinuity. Now, it's okay to abbreviate, but make sure your abbreviations make sense. It's good to abbreviate when the words are really long or you don't know how to spell them, right? But don't just put jump, like jump what, right? It's jump discontinuity, and then you have to say where. So it's at x equals what? -5. Good. Did y'all come from like the portables or something? Okay. You have 3 pieces of paper up here and an envelope to grab. Okay. Number 2. Is number 2 continuous or discontinuous? Okay. Oh, did you have a question? Kind of clarify. Oh, got it. Yeah, okay. Because it's at the x value. So yes, when you look over here, that's where it jumps right there at x equals -5. That's a good question. All right, and then y'all said that this is continuous. Okay. All right, all 3 pieces of paper, even the green one, and grab an envelope. All right, so you get the idea there? Now I want you to do 3 through 6 on your own. You can talk about it at your tables if you need to. I know if you just walked in that you may not really have a clue what we're doing, but we'll get you caught up. It's fine. Okay? Yeah, do 3 through 6. It won't take you but a second. So if I call on you and you just walked in and you have no clue what's going on, just let me know because I'm still not very comfortable with everybody's name and I'm not trying to like put you on the spot or anything. All right, so let's see. Where is Juan? All right, so Juan, tell me about number 3. Is it continuous or discontinuous? Okay, what kind? Okay, very good. So infinite discontinuity, where, Juan? At x equals 1. Do y'all agree with that? Yes, good job, thank you. And that's because there's a vertical asymptote there, right? Now, there's another asymptote on here. Is it a horizontal asymptote? No. What kind of asymptote is it? Does anybody know? Okay. All right, there's actually 2 different names. It can be a slant asymptote or an oblique asymptote. It can be called either thing. So you may not have learned those. I don't think you talk about them in on-level algebra 2. I think it's only pre-AP. I could be wrong about that. But if that looks like something you've never talked about before, it's okay. I'm just a little foreshadowing. I'm just telling you we are going to talk about them. Okay, and they do exist, even though you may not be familiar with them. Okay, thank you, Juan. All right, let's see. Cassie, tell me about number 4. Is it continuous or not? It's what? Continuous. Y'all agree with that? Yes. All right. Christian, tell me about tell me your last name, not Wong. Say your last name for me again. Harigi. Okay. I knew it was not that bad, but my brain. Okay. So tell me about number 5. Is it continuous or discontinuous? Okay. What kind does it have? Removable. Okay. So we have removable. Discontinuity, where? Good, x equals -3. And there's a few of these graphs where like people are giving me the wrong numbers every now and then because I think it's hard to, you kind of lose where 0 is. The x and y axis are not that much darker, and every now and then some random line is darker. Make sure you look for the arrows. If you look for the arrows so you can know where, you may need to darken the axes to make it easier for you to count. So I just forgot to say that. I want to throw that out there. All right, so then Eva. It is Eva, not Ava, right? Say it. Is it Eva? Okay. All right. Oh, you just walked in. But do you have the hang of what we're doing or no? It's all good. So instead, Eduardo's going to help you out. Tell me about number 6, Eduardo. What do you think? Okay. Okay, so we have removable discontinuity. Where? Yeah. I know this line looks dark, but look, that's one of the reasons I said that. There's your axis. Like, I think you know what you're doing. I think it's at x equals 4. Yeah, okay. Yeah. Well, he's not done. Just be patient. All right, Eduardo, do you have more to say? Yes, okay. And infinite? Jeez. Infinite discontinuity, where, Eduardo? X equals 2, yeah. I know, that line looks dark, and I don't think it's just because it's an asymptote. I don't know what the deal is. But yes, this has both, all right? So one of the things that was asked of me earlier today is, can I say it has removable and infinite at x equals 4 and x equals 2? You have to be very careful how you say that, because if you're not clarifying which is which, that's a problem. So if you say it a little bit differently, or if you put infinite first, that's absolutely fine. But make sure that however you answer it, it's clear that x equals 4 is the removable and x equals 2 is the infinite. Okay? Does that make sense? Any questions? Easy enough? Really is that easy. There's no crazy tricks to that. All right. I'm not lying. All right, on the back. So now we're going to look at end behavior, okay? So end behavior. As x moves towards positive infinity and negative infinity, end behavior describes what is happening to the value of f of x. Okay? So as x is moving to the infinities, what is happening to y is what we're looking at. So the way you read this is, as x approaches infinity, f of x approaches blank. So when I look at this, as my x's are getting bigger and bigger and bigger, so as x approaches infinity, what is the value of f of x approaching? Negative infinity. Good. And then as x approaches negative infinity, so as my x values are getting smaller and smaller and smaller, the value of f of x is approaching what? Infinity. Okay. Does that make sense to you? Here's the thing that you have to remind yourself of so you don't try and make it more complicated or get confused. This is end behavior. End behavior. I don't care about what's happening in the middle. All right? Whatever here, increasing, decreasing, intercepts right now, don't care. It's all about what's happening at the ends. So eventually we're going to take the end behavior, we're going to take the discontinuity and the intercepts, and we'll be able to sketch some graphs and know the shape of them even if we can't find exact values. So if all I knew about a function was this right here, then when I go to sketch it, what I know is that as x approaches infinity, f of x approaches negative infinity, and then as x approaches negative infinity, f of x approaches infinity. I know the end behavior looks like that. Then I would have to do something different to be able to find, to see if I have any holes or discontinuities, figure out where my intercepts are, and figure out what's actually happening in here. Like, does it just go like this, or is there like squiggle, like all that you find differently, but I at least have the end parts. Okay, does that make sense to you? End, we ignore the middle. All right, so let's look at these examples. It says, describe the end behavior of each graph. Now you have to do a little bit of writing, but you'll survive. All of my students have survived this all day long. So as x approaches infinity, this is when we're thankful for the symbols because we don't have to write all of those words, right? F of x approaches what? So as x increases, as x approaches infinity, the f of x value approaches infinity, not negative infinity. So good. Now as x approaches negative infinity, f of x approaches, what do you think? Infinity. So as x gets smaller and smaller and smaller, the y values are getting bigger and bigger, approaching infinity. That makes sense? We good? All right, so I'm going to give you a minute. I want you to do 8 and 9 on your own, get it all written out. All right, Yohida, can you help me with 8? Can you read that for me and tell me what you think the answer is here? Negative infinity? Okay, so I've actually had that phrasing a lot today. Are we ever going to reach negative infinity? No, so we're approaching. So you gotta be careful with it. Because there's a difference. Like you can use different words sometimes and it's fine. Like if I said exactly 1 and you said only 1, same meaning, right? But approaching something and actually reaching it are two different things. So and I know this is new and it's just symbols, so you have to learn how to read it. So it's as x approaches infinity, f of x approaches negative infinity. So that's good. So go do the second one for me. Yes, very good. All right, y'all okay with that? Yes? All right. What? Did you know? Oh, I thought you said you weren't. That's what I went. All right, so since you were so okay with that one, help me with 9, Tony. All right, so I'm good. Glad you're okay with that too. Okay. All right, so there was some question on this one, and I've had some questions on this one all day. Now, is this discontinuous? Yes. Do we care right now? No, okay? It is discontinuous. We have some asymptotes. We have all kinds of things going on here. But all this is asking me about is in behavior. So remember, the middle, don't care. I can ignore all of this stuff. I can cover that up. But then as x gets bigger and bigger and bigger, what's happening to y? And as x gets smaller and smaller and smaller, what's happening to y? Does that make sense? So if you find yourself like overthinking it because there's a lot going on, you can literally cover it up and just think about the ends. Because I see why that can kind of get confusing. Does that help? Does that make sense? Everybody else good? All right, so these are all about the infinities, right? So it doesn't always have to be infinity. Let's see what happens with the values here. So as x moves towards positive infinity and negative infinity, it's possible for f of x to be approaching a certain value. Because infinity is not a value, it could, but so we could be approaching a number. So if we look at the end behavior over here, this graph, as x approaches infinity, what are the y values approaching? -1, because this has asymptotes, right? Here I have a horizontal asymptote that actually helps me now. The vertical asymptote doesn't do anything because that's middle behavior, don't care. Horizontal asymptotes give me in behavior. So it's never actually going to reach -1, but it's approaching -1. So then as x approaches negative infinity, f of x is approaching what? -1. It's just from the underneath. Okay, does that make sense to you? All right, so let's look at 10. Say as x approaches infinity, f of x approaches, what do you think? 0. So as x is getting bigger and bigger and bigger, the y value is approaching 0 because that's a horizontal asymptote there. So then as x approaches negative infinity, f of x approaches what do you think? 0 also, yes. Now I want to look at this. There's a little side note about this one though. Doesn't necessarily have anything to do with what we're doing here. But I don't know how, it looks a little bit better on your paper, but here it looks to me like this is coming up and it's like hugging the bottom part of the x-axis because I can see the little arrow right here. On this side, it looks like it's coming up above the axis a little bit and then hugging the top side because I can see the arrow right there. So can you cross a horizontal asymptote? What did you learn about asymptotes? That you never actually touch them, right? You never actually get there. The truth is, for a horizontal asymptote, you can cross a horizontal asymptote. You may not have seen a function yet where that happens, but it can happen. Vertical asymptotes, no. And so this is just, again, a little foreshadowing, so we'll talk about them later. But if this comes up and gets greater than 0, but then it's coming back down, in the end, because I only care about in behavior, it's approaching 0, and that's what really matters. Okay? Does that make sense to you? We good? All right, so I want y'all to do the last 5 on your own. Write them out. Talk about them if you need to. All right, number 11. I don't mean to try and rush you, but I want to have you do a couple things for ISN at the end. So, Alex, can you help me with number 11? Approaches. Mm-hmm. Okay. Okay. Do y'all agree with that? Yes, because it's approaching -3. Remember, it's not about what's happening up here. It's about what's happening out here, and it's going to get really, really close to -3 and never actually make it. Good. Thank you. All right, number 12. Let's see. Rudolph, help me with number 12. Okay. Okay, y'all agree with that? Yes? Okay, good job. If it helps you to draw in the asymptotes, you can. You don't have to, but it's the horizontal asymptotes that are helping us here. There's a vertical asymptote too. Don't care. That's middle behavior. Not worried about that. All right, 13. Let's see. Christian Wong, you want to help me with 13? Okay. Okay, that's negative. Y'all agree with that? So there's been some confusion on this one too, because somebody was asked me, well, isn't this in behavior too? No, again, this is middle behavior because I can cover all this up. Now, there is a limit here, and we are getting into talking about limits. So as x approaches 3, then the y value is approaching infinity, but I'm not asking you about that. I'm asking you way out there at the end when x is really, really close to infinity, what's happening to y, and that has absolutely nothing to do with that stuff there. Okay, we good? So you just cover it up. All right, 14. Let's see. Jose Sanchez, 14. Okay. Okay, y'all agree with that? Yes? All right, awesome. All right, Davian, can you help me with 15? Infinity? Okay. Okay. So, y'all agree with that? Yes or no? Okay. Who says no and wants to give me a reason why? All right, Sebastian, help me. It's flipped. So as x approaches infinity, as my x's gets bigger and bigger and bigger over here, this is when y is actually approaching that -5. Does that make sense? So this is actually -5. And then as x approaches negative infinity, right, when my x's get bigger and bigger and bigger, the y values are approaching infinity. Okay, does that make sense? Okay, any questions? Now, tell me, as you got to number 14, what were you thinking about your answers? Like, were you thinking they're always going to be the same? I mean, you might have been thinking that before 14, or at least had that question. And then you got to 15, and it might have thrown you off a little bit, at least for a second, like, wait a minute. Now, if I had only done the first, like, 4 or 5 examples and never said whether or not they were the same, y'all would have left here. Some of you would have had that misconception that they're always the same. Even though you may not have, like, consciously come to that conclusion, that's all you ever saw, you're probably thinking maybe that's what it should always be. So that's why you kind of need to see it from different angles and never assume anything unless you can prove it for sure. So are we good? Any questions at all? Awesome. All right. So we're going to put together our ISN a little bit.